Alright, so we got a relativity problem here. And we're given the length of the train. Now, the formula, the way it works, is that we say that the length of the train in the train's frame, that's the proper length, is equal to the length measured in the, I guess we could call it the rest frame, divided by gamma, right? So that if you're on Earth, if you're watching the train go by, oh wait, I take that back. Sorry, it's got to be multiplied. If you're on Earth, then you're going to measure a shorter length. If you're on the train, you're going to measure a longer length. So gamma is equal to the proper length of the train, which is 350 meters, divided by how long the train appears from Earth. Okay? Gamma is always greater than 1. In this problem, you could just guess. It has to be 350 over 220. Can't be 220 over 350 because that would give you a gamma less than 1. So gamma is 1.59, and that's equal to this whole mess. Now I've got to extract v from this. So I'm going to square both sides. So 2.53 is 1 over 1 minus b squared over c squared. And then that becomes 2.53 minus 2.53 v squared over c squared equals 1. So v squared over c squared is equal to negative 1.53 over negative 2.53, which is 0.6045. So v squared is equal to 0.6045 c squared. So v is 0.78 c. So we're going 78% of the speed of light here in part A. Now, part B, how fast does it move for an observer in 500 nanoseconds? So we say the distance measured in the rest frame is equal to the velocity times the time measured in the rest frame. Now the velocity is 0.78 times the speed of light. And the time is 500 nanoseconds. That's 500 times 10 to the minus 9 seconds. So that's 120 meters. Simple as that. Just make sure that your distance and your time are both measured in the same frame. Now on board the train, how far does the train travel, right? So basically, what's this 120 meters? I guess there's a couple of ways to do this, right? You could say, you could think of this as a train, for an observer, if you lay down a 120 meter tape measure, then the train goes from one end of that tape measure to the other. But now an observer on the train sees that tape measure, and the tape measure appears to be contracting, right? We would say that the length of the tape is equal to gamma times the length as measured in the train's frame. Right, that's the weird thing about relativity and length. The proper frame depends on where the tape is, right? So anyway, you could use it this way. You could say that the length of the tape is equal to gamma times the length in the train frame. So the length as measured in the train's frame is 120 divided by gamma, which is 74 meters. Another way you could look at it is you could say, well, how much time passes on the train? Maybe this would be easier, because the time dilation isn't so bad. You could say, well, how much time is measured on the train? Well, the time measured on the train is equal to the time measured in the rest frame divided by gamma, right? Moving clocks run slow. Less time is going to pass in the train's frame. So I take 500 nanoseconds and I divide by gamma, and that gives me 314.5 nanoseconds. That's how much time passes in the train's frame. So the distance measured in the train's frame is equal to the velocity times the time measured in the train's frame. So if I take 0.78 times 3 times 10 to the 8 times 314.5 times 10 to the minus 9 seconds, I get 74 meters. So either way you go, you're going to get the right length.